Morning. So, let's see, where did we stop last time? Last time we stopped section 12.2 on the polar coordinates. And in polar coordinate, most important polar coordinate is that we use x equal r cosine theta, y equal r sine theta, and these two. So those formulas together will convert from the polar coordinate of r and theta to a rectangular of x and y. Right. And so we can convert the point to polar. The only thing that we need to worry about is that when we use the tangent inverse, make sure that have to be in the right quadrant. Whenever we use this, make sure it is in the right quadrant. If it's not, we have to add a pi to it to bring that to a right quadrant. Right. And we did this example where we convert a bunch of equations from polar to equation of rectangular of x and y. So we have the equation, then we have all that, and we stop where we have we did this example. Right. Now, just want to show this real quick. Let's say if you want to graph the equation in polar coordinates, let's say that one for example, how would we graph it? So first of all, this is in polar because I have r and theta, so hit mode and make sure that in polar, so go to polar, and by default, if they not mention anything, it should be in radian mode, so radian mode and polar, and then we enter r equal to 6 sine theta. Of course, then we see the graph. Right. If we actually want to see the more accurate graph, because as you see, this graph go from -10 to -10 to 10 and -10 to 10, and horizontally, the axis is, it is wider on the horizontal than the vertical. So if we want to make it kind of a square, zoom, go to number 6. In that case, sorry, not number 6, number 5. In that case, they have the same axis. As you see, the increment on x and y will be the same. So we have that. Now, that's one thing. The second one is more important. That when we graph is in, whether it is in polar or parametric equation, we have to see where the graph goes. So if we want to change, this will be from 0 to 2 pi, 0 and then 2 pi. That easy. The theta will go from 0 to 2 pi. Now, depends on how fast or slow we want this to go. If we just say from 0 to 2 pi, let's say I only need to graph 20 points. So the length of 0 to 2 pi divided by 20, so we will graph 20 points, pretty much. It will go very fast. We won't be able to see the graph accurately. Now, if we hit Windows, rather than we graph 20 points, the length of 2 pi, now we divide into, let's say, 100 points. It will go slower, and we will see where it starts and where it ends. Slower. If we want even slower, and we see the graph where it starts and where it ends. So it is a circle. And we see it is the circle radius 3 and the center 0 and 3. Right. So that is polar equation. If we want to graph parametric equation, same thing. Let's say we have 2t and t squared plus square root of t. And let's say t go from 0 to 5. In that case, take 5 divided by 100. So we will graph 100 points. And then we'll see where the graph starts and where the graph ends. So hit the windows, change the parameters, and it will graph it. If we want a bunch of points, so we actually see the movement of the graph go very slowly. Divide by a bunch of points, use a bunch of points, and we should be able to see the graph. Right. So that's what I just want to show real quick. How do we graph it? So it doesn't matter whether it is in polar or parametric. We can always graph that. Make sure you go Windows and change where the point, where you start, when we end, and how slowly we want to graph the function. Right, so we did this. Now we will convert this equation into a polar equation. We continue on this, and what's that? 2. So we'll convert the following to polar equation. First we have y equal to x squared. Right. I go back and see what do we need to go from polar rectangular to polar, or polar to rectangular. We need to have this formula: x equal r cosine theta, y equal to r sine theta, and then x squared plus y squared equal to r squared, and then tangent equal to y over r, y over x. And note that when we use this, make sure that it is in the right quadrant. Right. So y is going to be r sine theta, x squared, x is r cosine theta, and we have the square. Square go to r, square go to cosine. Right, and then we can divide 1r on both sides. So we have sine theta equal to, cancel out r cosine square theta. Right, so that's certainly the polar equation. It is equation, so it doesn't have to be in any particular form. If we want to, we can divide by cosine square on both sides, and we have r equal to sine theta over cosine square. Right, simple enough. 2. Y equal to 3x plus 1. So y is r cosine theta I mean, I did say cosine, right? So r sine theta. X is r cosine theta, and of course 1. So we have r sine theta equal to 3r cosine theta plus 1. Of course, we can stop at this step, or we can solve for r and move it with one side, factor out. We subtract this to the other side. And factor out the r. And then divide by it. Right. So with that. X squared plus y squared equal to 5. Right. So x squared plus y squared. Of course, x is r cosine theta, y is r sine theta. We can just substitute in. That easy. However, even easier is x squared plus y squared is r squared. So here we have r squared is equal to 5. Taking square root on both sides. We could choose plus square root of 5 or negative square root of 5. It doesn't matter. Right. Now, of course, we still graph in polar. So the reason that we usually solve for r is that the graph will work out better. Let's say in polar. Say we want to graph this one example. Square of 5. It's no big deal, right? We just graph. Right? The problem. However, how about if we have negative square root of 5? Still graph the same thing, right? Let's zoom in and see. So the graph starts from this point and go there. Right? Now, if we change to positive, the graph starts here and then goes there. Right. So we still have the same graph, but depends on the theta. When it go from 0 to 2 pi, it will graph differently. So it's very important on the polar coordinate when we try to graph, the starting and the end point. It's important because when we look at the graph like that, we don't know where it starts, where it ends. But the parametric equation or polar equation, we can see where the graph starts and where it ends. Right. Symmetry in polar equation. We will not emphasize this, just so that there will be some form of symmetry. Symmetry with respect to the x-axis. With respect to the x-axis is the polar axis, or the line pi over 2, or with the origin. So we're not focused on that, because now we have, after we can just graph them, and we see, I just want to graph the last one here. Exponential sine theta minus 2 cosine of 4 theta. Oh, it looks like butterfly, I guess. Just zoom out and see. So, of course, when we see the graph, we can see the symmetry. But bottom line is three forms of symmetry with respect to the polar axis, with respect to the line theta equal to pi over 2, and with respect to the pole. Right. We more focus on section 12.3 about the calculus of polar coordinates. Because after all, this is calculus. Calculus in polar coordinates. 1. Slope of the tangent line. Two. Let f be differentiable at a point theta. The slope, pretty much the slope is the derivative, right? Of the tangent line to the curve. And the curve given by polar equation r is a function of theta at the point. Now this point is in polar coordinate. Yes. So when we write this point, this is in polar coordinate. Now when we write the slope, we actually write the slope in rectangular form. Right. F theta sine F theta cosine then F prime cosine minus F sine. And of course when we divide, the denominator is not equal to 0. Right. And provided the denominator not equal to 0. Right, and we will see this later. At the point where the function equal to 0 and the derivative not equal to 0, we have the tangent line go through the point. Yeah, that should be 12.3, sorry. Yeah. I guess I typed that wrong. So we have the function is equal to 0 and the derivative is not. The tangent line is theta equal to theta 0. And because when we write like that, the slope equal to, we take tangent on both sides. Our slope is tangent theta. Not. And most importantly, this line go through the pole. And by the pole in polar corner, I mean the origin. Right. So first of all, where's that formula? Where does that come from? Right. So to do that, let's look at the proof rather quickly, because that is actually a lot simpler than what we know. So let's put everything we know together. First, bottom line is we're trying to find dy over dx, right? Now this proof will reveal everything we have up to this point. Let's say if we have y is a function of t and x is a function of t, right? X and y are a function of t. Then we're going to write like that. dy over dx, y is a function of t, x is a function of t. What if what if we divide by dt, top and bottom? So we will have dy over dt over dx over dt. Simple enough, right? That's what we have. Now, if we have theta, next what we do is in polar corner, if we have x equal to r cosine theta, and y is r sine theta. Most importantly, in this part, we have to assume that R is a function of theta. Right. So how's that significant? Right. Then we go back and use that formula. dy over dx is going to be, now all of them are function of theta. So we have x is r cosine theta, y is r sine theta, and r is a function of theta, meaning that everything are function of theta. X and y are function of theta too. So now we will have, instead of dy over dt, dx over dt, we will write dy over d theta dx over d theta. So, and y is this, and x is that. So I substitute that in. R cosine theta. R sine theta for y, and r cosine theta for x. And notice that since r is a function of theta, so we have to consider that as a function of theta, and we just use the product rule. R prime sine theta plus R, then we take derivative cosine theta, and then R prime cosine theta plus R, derivative of cosine is negative sine theta. So pretty much we will have R prime sine theta plus R cosine theta, R prime cosine theta, subtract R sine theta. Right, that's pretty much it. The only difference here is they said R is a function of theta given by function f. Now, so when we say R is a function of theta, we mean R is a function of theta. So in that case, R prime is derivative of f with respect to theta. So pretty much, if we replace this into this, we have that formula. All right. Now just replace this into R prime is derivative of f and then divide by so just like that. It's not that bad though. However, usually when we find derivative, we're not going to do this. Definitely, we're not going to do all of that, and we're not going to memorize that formula either, because we just find x and y first, and then what formula we use is going to be actually this. But the way we do it is kind of similar to the proof. That only time. Alright, next, let's go to an example. Sorry, if this is B, this must be C, and this is D. No, I just missed numbering them. So C, example 1. How far the slope of the tangent line of the tangent to the circle are equal to f of theta equal to 10. Right, so if we want to graph r equal to 10, it is a circle starting from here. Get back to that. Right, so what do we do first? By the way, I said the actual formulas is we use dy over dt or dx, and then over dx over dt. Now if we have the function of theta, so we have dy over d theta over dx over d theta. So actually this is the formula that we use, and not that complicated one, and definitely we're not going to derive the formula again. So again, let me just write this: dy over dx is dy over d theta over dx over d theta. Just like that. Now we just need to know what is x, what is y as a function of theta. So we start with, as always, x is equal to r cosine theta, and y is equal to r sine theta. Now r is equal to 10. So this is just 10 cosine theta and 10 sine theta. So the derivative, we're going to have derivative of y. This is y. With respect to theta. Now we know that it is theta, and we just take derivative with respect to theta. And over x, this is x with respect to theta. We just do that, right? So derivative of sine is cosine and the derivative of cosine is sine. and cancel out 10 and 10. Have cosine over sine, which is equal to cotangent of theta. Right? So let's think about that. So we have a circle, right? By the way, that is the answer though. That's what we do. I just sort of wonder where the derivative is. It actually have a compass, so you probably don't see that at all, but let's just so that's a circle. Raise 10. I think about, and the graph actually starts here, and it go in that direction. So go that direction. So let's say if we have this point at this point, that is theta equal to pi over 2. And if we put pi cotangent of pi over 2 here, what's that? Cotangent of pi over 2 if we cannot enter cotangent, use the fraction. Cotangent is cosine over sine. So that is 0. So the slope is equal to cotangent of pi over 2, which is equal to 0. And that is the slope. And at any point, so for that point, this is like 3 pi over 4. The slope is equal to that. Why is that positive? Yeah, that's why I check. So when theta equal to 2, the slope is actually -1. So indeed, I forgot the negative sign. So good thing we actually check with the graph. Sorry, derivative cosine sine. Right, so it works. By the way, This is not dx. This quantity though is, I know it's bad, dy over d theta is equal to that, and this one is dx over d theta. So this actually, when we talk about the better way to write the formula, is just y prime of x prime is a function of theta, and that's what it is. So this is not dx. So sometimes it's help to actually check the answer. Again, just find x and y first, and then just y prime over x prime. As long as x and y are function of theta, we're good. Okay, so thanks. Actually, you pay attention. Right. Find the points on the interval negative pi less than equal to theta less than equal to pi, at which the carryover has a vertical or horizontal tangent, and the carryover is given by r equal to the function of theta 1 minus cosine theta. Right. Now if we want to see the graph first, 1 minus cosine theta that's good. Let's zoom in because we barely see it. Right, so that's good then. However, actually it's not. Remember, we go from negative pi to pi, so negative pi go to pi. The curve still the same, but this will tell us where the graph actually starts. So we start here, go counterclockwise, and have a carryover. Right. So same formula. Derivative of y over derivative of x. Right. So we do that. But first, find out what is x and what is y. So x equal to r cosine theta as always. Y r sine theta. So this is the relation between polar and rectangular coordinates. R is 1 minus cosine and times cosine. R sine theta is 1 minus sine times cosine. Alright, so we have x, we have y as a function of theta. Put it back in here. That's pretty much it. Now when we take the derivative of this, we use the product rule. Alright, so this is u, this is v. So u is 1 minus cosine and v is cosine. So that is at the top what we're doing. So derivative, now let's just write down one more time. 1 minus cosine theta, derivative 1 minus sine theta, man, just copy from one place to another. Sorry. Yeah, put on this one. So this will be cosine. Sorry. R is 1 minus cosine and R times sine theta. Right. So this is R times cosine, R sine. Right. So we good. Now we take derivative and using the product rule, so this will be a little long. So derivative of 1 minus cosine u prime, derivative of negative cosine is sine. So u prime v plus u v prime, derivative of cosine is negative sine. And then the bottom multiplied out, I mean not multiplied out, but using the product rule here. That is y, or this u prime, derivative of that, derivative of negative cosine is positive sine. And then times v plus u and v prime, derivative of sine is cosine. Right, multiply it out. Sine theta, cosine theta, minus sine theta, and cosine times sine, negative times negative, positive. And then we have sine square plus 1, no, not plus 1, sorry, plus 1 times cosine that's times cosine minus cosine square. Alright, simplify 1 and 2, that make it 2. And then at the bottom, sine square minus cosine square, that is not an identity, but since there's a cosine here, we will substitute so sine square 1 minus sine cosine square. Substitute into that, we have 1 minus cosine square plus cosine minus cosine square. So I have 2 sine theta cosine theta minus sine theta, and then cosine square and cosine square make that 2. 1 plus cosine theta minus cosine square theta. Right. So if we want the horizontal tangent, the top is equal to 0. If we want the vertical tangent, the bottom equal to 0. I got the back one. Dang it. Yeah, because I want that one on the top and that one on the bottom. That's why I do that. Never mind. Sorry, that was wrong. So y prime is actually this one. And x prime will be that one. Yeah, because I write that one first and that one on the top, that one at the bottom. So I just divide them. Right. Again, should be that. Right. The good thing is I think I do this correctly, so I just flip this real quick, but I just do that again. So u prime v plus u v prime u prime v minus plus 1 u and v prime. So sine square and then the bottom sine theta cosine theta minus sine theta and plus sine cosine. So that make it 2. And the top sine square we do the same thing. That yeah. And good thing is I make this mistake so on the test you don't have to. So think about that. Right, and then of course that's simply fine. Right, so That is the slope or the derivative. Now, on the homework we see this quite a lot. They give you theta equal to a point and we then put that in. So for example, if we have the slope equal to pi over 3, then we just put pi over 3 into this and evaluate. So just like that. Yeah. For the homework and the test, you will see a lot of them. Just let theta equal to something, and then we evaluate the slope. That part is easy. Now, finally, so horizontal tangent line. That's where the top equal to 0 and the bottom is not equal to 0. Vertical tangent. Vertical tangent is where we divide by 0, so the bottom is equal to 0. And top is not. Of course, if the top is not 0, the bottom is not 0, divide them. That's not equal to 0, not any significant. My point is, what happened if both of them equal to 0? In that case, what we have is indeterminate because 0 divided by 0. So that could be anything. Usually, if the top and bottom equal to 0, the graph will missing a point. But that we're not talking about the graph. So that's one. If both of them equal to 0, that means there's something to simplify. And usually it will be cancelled out. So I'll give you on the easier example. So when we have the equation x minus 1, I mean the function if this is the function and both of them equal to 0, so they just cancel out. So when both of them equal to 0, that means there's something to simplify from the top and the bottom. And we don't know what it is, so just put a question mark there. Right, let's write the formula for the next part, and then we come back after the break. Area of region bounded by the polar curve. Right. Now, let the region R, this is the script R, be the region bounded by the graphs of R equal to f theta and R equal to g theta. In Calc 3, this will be a little more complicated. But for now, theta are constant. Between alpha and beta, f and g are continuous. and we have the function f greater than equal to g and greater than equal to 0. On the interval alpha beta, then the area is when we go to, if we go to count 3, then we don't even need to memorize this formula. But for now, proving this without count 3 is very difficult, so we don't. So multiply this. Try to sketch the graph. You see the graph is bounded by two. This one theta equal to beta, and this one theta equal to alpha. So the graph is between this, and there's a two curve. One from the inside, this is f of theta, and the other one on the outside. And we're talking about this area. The easiest example is we talk about the concentric circle. Say if we talk about the area of this sector, and then the big area, say the radius 1 and radius 2. So the area of the sector is pi r squared. It's the whole circle, and then we have 1/4 of it inside, and on the outside is 1/4 pi big radius square minus that. So if we talk about a quarter of a circle, if we talk about the difference of the area, if we talk about this area, then the big sector minus the small sector, and we just have this. By the way, the reason we have the 1/2 here because the area of the sector is 1/2 r squared theta. This is the area of a sector. Right. Take 5-minute break here. We continue at 9:11. 5 minutes from now. Remind me, on the second break, at about 10 o'clock, I will send out a collaborate link, and you can sign in and see if it works or not. Let me write this real quick. So we send out the link where we can check the final. So you can sign in for the final exam at about 10 o'clock. So you can see, try to log in that either with your cell phone or with your computer and see if it works. Of course, on the actual final, I will send completely different link. Originally, I thought I would use Zoom, and then I got an email from school recommend that we're not using Zoom anymore because of the Zoom bombing. So that's why I have to switch to that. Right. One more minute. Yeah, this now. B. Example 1. Find the area of the 4 leaf rows. Just copy from one place to another. Right. 2 cosine 2 theta. Right, sorry. Now, on this problem, I highly recommend that we actually graph the function before we find the area. And also, even though if it is on the test or on the homework, read the question very carefully. Especially on the test and the homework, read the question carefully. Whether I want the area of the whole 4 leaves or just want the area of one petal of the rose. I could want the whole thing or just want one of them. It's very important. Right. So first, how do we graph this? Of course, we enter the function 2 times cosine 2 theta. Yeah, graph. So, 1 petal. By the way, that looks a little off. Now, actually remember, s go from 0 to 2 pi. So actually it start here and it go like that. And definitely the graph does not go like this. Let's see that again. How do we reset the graph? Okay, yeah, just turn it on, turn it off. Right then. Let's sketch, draw the sketch on the graph. Just sketch the graph and see what do we have. So look like this is 1 and 2, so the petal go to 2. Alright, go. I just forgot that again. Okay. Go to equal sign, enter, and then enter again. So turn it on, turn it off. Turn it off, turn it on. Okay, got it. 1, 2, 3, yeah. Of course, it should be better than this. Actually, when we draw it, maybe we just draw one petal at a time. It will be better. Even though that's not the way the graph goes. Probably better. Anyway, so this is the graph. And now the area of 4-leaf petal. So when we look at this, we see we want the area of 4 of them, right? How about we just find the area of 1 of them and multiply by 4? Or better yet, even for each petal, it is symmetry. So why don't we just want the area of 1 petal, half of a petal, and multiply by 8, right? So, and usually a picture tells 1,000 words. If we want the area of that, it's going to be 8 times the area of half the petal. I mean that. Yeah. So a picture tells 1,000 words. You want that area, just find that, multiply by 8. Because of symmetry, that is. Of course, you can say 4 times a petal or 8 times half a petal, either way. Right. Now, so how do we set up a petal? Right. So in that case, we have to find the limit between alpha and beta. So we will look at the interval from here to there. Right? So how do we find it? So in order to find the interval of half the petal, we need to do earlier. Remember, this is where we have the tangent at the center. So the function equal to 0 and the derivative is not equal to 0. So the first thing we do, of course, is no calculus at all. Need to find where the petal breaks. So what we do is we're going to let r equal to 0. And then r prime not equal to 0. So where's that come from? Here. At angle edge width, the tangent line is when the tangent line goes through the origin. When that is the case, function equal to 0, derivative is not. So that's what we got that from. So when we do this, to get the boundary. Of the rose petal. Right. So let derivative equal to 0. I mean function equal to 0. And divide by 2 on both sides. Cosine of 2 theta equal to 0. Now cosine equal to 0. Where is that on the unit circle? Cosine equal to 0, we have this point and this point. So pi over 2 or 3 pi over 2. Or we just say in general is pi over 2 plus 2 k pi. A period of cosine 2 theta is 2 theta is theta. And then divide by 2 on both sides. So we have pi over 2 divide by 2 pi over 4. This divide by 2 k pi. So what we have is the 4 boundary. Pi over 4. Pi over 4 plus a pi. 3 pi over 4. Pi over 4 plus, when k equal to 2, we have 5 pi over 4. And 7 pi over 4. So we have the boundary of each petal. Of course, we just make sure that this doesn't make the derivative equal to 0. But that looks good enough. So now if we want the area of one petal, we can just manually change this. Let's say pi over 4 to 3 pi over 4. So we have pi over 4 to 3 pi over 4. And when we graph, we exactly have one petal. And then we find the area of that multiplied by 4. Or better yet, find the area of half a petal multiplied by 8. So how about half a petal? Obviously here's where theta equal to 0, right? So we go from 0 to pi over 4. Make sure it works. 0 pi divided by 4. Do we have the half petal? Yes, we do have the half petal. So yes, so the integral here is going to be a times the integral. We will go from 0 to pi over 4. And something d theta, which to be determined. Right, so this on this problem we actually have to graph it and see is the interval correct. Is that the area we want? Right. Now try to draw this on a bigger scale. We only have half of the petal. By the way, you can do from 0 to pi over 4 or pi over 4 to pi over 2. Pretty much there's a bunch of way to do this. I choose 0 because that is easier to evaluate. Remember, on the question, on the example, on the test or on the exam, read that carefully. Do we want all 4 petals or we just want 1? Now, write a little bit bigger. Now, in the formula is that, right? So let's say we have the area is equal a times. At least we know it goes from 0 and pi over 4. Now let's general say 1/2 the outer function minus the inner function. Remember the 1/2 multiply to the whole thing. The inner function. Right. In general, that's what the formula is. Now, that is the big radius, that's the little radius. Now, how do we determine that? So, the way we do this is it's all about the perspective. If we look from the center and we look outside, what do we see first? If we see this function first, that is the inner radius, and after that we see this function, so that is the outer radius. Same thing here. We look from the center, that's where we looked. On the outside, what do we see? We don't see any function from the inside. We know inside is 0, and we go all the way to the function given by r equal to 2 cosine theta, cosine 2 theta. That is the outer function. Let's look at another point. From here, go on the outside, the only thing we see is the function. Doesn't matter how we go by. So the outer function is this, and the inner function, we don't have it, 0. So this function is that. And because we go from the center, we don't see any function from the inside, so there will be none. In that case, we'll let this equal to 0. So the total area of 4 petals is going to be 8 integral from 0 to pi over 4 1/2. We have that. And that. So which will be equal to 8 times 0 to pi over 4 1/2. I'll multiply this out. 2 square is 4, and then cosine square 2 theta. And then take all the constant on the outside. We have 8 1/2, and then 4. Multiply all of that. 8 times 4, 32. Divide by 2, 16. And then cosine square. Right. Now how do we evaluate cosine integral? Integrate cosine 2 theta. Right. So go back to section 8.3, trigonometric integral. When we have an even power, the only thing we can do is using the reduction power. So in this case, these formulas are very important. If we have cosine square, I'm not going to use theta, just use u. It's going to be 1 plus cosine 2 theta 2u divided by 2. And when we have sine square, 1 minus cosine 2 theta So cosine is a plus, sine is minus. Right, so in that case, I'm going to use that formula there. 16 to the power of 4. So what I actually do is I'm going to put that in here. So in the formula, I hate when that happens. This will be u. It's not wrong, but just want to be consistent here. Right, cosine square. We're going to use this formula. So what we actually do is, from the angle, it's going to be double the angle. So we double the angle and reduce the power. Power reduced by 2, the angle is double. By a factor of 2, I should say. So here, instead of 2 theta, it's going to be double the angle, 4 times theta. Let's split 1/2 and 1/2 cosine of 4 theta. And then we integrate 16. Integral 1/2, there's a constant. Just have 1/2 theta. And integral cosine is positive sine, right? But we have to divide by 4. Remember. So sine of k, cosine of k theta, so it's going to be, have to divide by 4. Now the limit go from 0 to pi over 4. Let's simplify all the fractions if we can. Multiply 16 in. 16 times 1/2 is 8. And then the 16 divided by 2, divided by 4, 1/2, 1/4, 1/8 times 16, 2. And then substitute the upper limit. A pi over 4. And subtract when we substitute in the lower limit. A is 2 pi. So 4 petals, there is 2 pi. If we only have one petal, then divide this by 4. Right? Remember, in the formula, there's an 8 because A times half a petal. We want the area of all 4 of them. So it's going to be A times half a petal. That multiplied by 8. That multiplied by 8. Now where the fun begins. I'm not going to integrate this because sometimes integrate this is a lot of complicated problem. However, it's just trigonometric substitution where we have cosine square and sine square in the integral. Using those two formulas will help. Now my focus here is to set up the area. Consider the circle r equal to 1 and the cardioid one plus cosine. Only set up, do not integrate. Set up the integral. That calculate one. The area inside the circle and inside the cardioid. Calculate the area inside the circle and inside the cardioid. So we have the graph of the circle and the graph of the cardioid. Again, we just set up the integral. Yes. So I assume that the problem is where to set up the area of one petal. So for this, we actually have to find where we have breaks the boundaries for one petal. So I set up the r equal to 0 to find where it intersects, because the way we draw a petal is going from 0 to 0. This is the way we draw one petal. So when r equal to 0 and then back to r equal to 0. So that's why we let r equal to 0. And in that case, we solve for it and we have those 4 values. So we know that one petal will go from that to that. Now, because of symmetry, instead of find the area of all 4 petals, we find the area of 4 petals. But even better yet, I will find 8 times half a petal. So knowing the graph is the key here. So we have to do that. And then when we have that, then we set up the problem is where it bounded alpha and beta, and then from the center looking out, if we see the function inside that inside circle, whatever function outside that outside circle, since we go from the center out, we don't see any function but this curve. So in that case, the outside function is that and the inside function is 0. That's what we have. Right. Next, let's try to graph the two functions, the circle and the cardioid. So the circle r equal to 1 and the cardioid 1 plus cosine theta. See the graph? Wait, never mind. Let's go from 0 to 2 pi. Right, so that's the circle. And that is the cardioid. Right. Try to graph it. Was that equal to 1? Have a circle. Okay, let's draw this in blue. At the circle, R go to 1. Now at the carry go to this point, 1, and then 2. It's not going to be good. Right, so we have that, a circle and a carry on. Right, so in this one we want the area inside the circle and inside the carry on. So inside the circle, inside the carry on. So it looks like this is the area, right? Now, it will not be easy. So first of all, how do we do that? Actually, the thing that's difficult here is when we look at this, there will be 2 parts. Always look from the center out and what we see. So from here, looking out in this direction, what do we see? The circle, right? The circle on the outside, and there's no tunnel. Now, so that's only for half of that. Now, if we want to make sure is that the area we want, go to the function, and I will turn off the second function, highlight equal sign, hit enter. Now, what is the interval? That gives us half the circle here. So let's say we go from 0. Actually, it's not 0. Here's negative pi over 2 and to pi over 2. Sorry. Pi over 2. And then pi over 2. Do that, we have half of the circle. And that's the area we want. So first, the area we have in this case, the area of a semicircle. That area, we don't even need any calculus, but if we do, remember negative pi over 2 to pi over 2, 1/2. Because from the center out, we only see the outer function. So we're going to put, if we use calculus, the outer radius is 1. There's no inner radius. It's going to be 0. This pretty much, if we do that, half of a circle, that should be easy. 1/2 pi r squared. Because this is a circle, so that one I can come up with this area. So this is a semicircle. Not bad, right? So now the bad part is we do have the little tiny bit here. So from that, again, we go from the center and looking out. from the center here, looking out, we see the red curve, right? Center from 0, only see the red curve. And that's all we see. Again, from the center out, I can go extremely close here. From the center going out, we only see the red curve. So in that case, by the way, those two areas are the same. We can say the area, the picture tells 1,000 words. We have the area of that. That portion is going to be 2 times the area of one of them, right? Right. So the area of that, this is going to be 1/2. Again, the outer function from the 0 on the outside. We start from the center. We don't see any function from the inside. We only see the red curve. So the red curve is 1 plus cosine theta. And then there's nothing inside. How do we determine the limit? Look like the limit go from here, which is pi over 2, and then it go back to this. So let's see. How about go from pi over 2? Just graph the second function. Right. It go from here, pi over 2, back to pi. How about go to pi over 2? So always have to graph and see if that's actually what we have. So you see the graph only have that part, so this is good. So if we go from pi over 2 to pi, we have that area. Of course, I forgot the 2. Right. So do this, and then add those two. We have the area of that part inside the circle and inside the carioid. Right. So again, the formula is 1/2 big radius square minus little radius square. The big radius is from the center to the outer radius. The little radius from the center from 0 to the inner radius. To determine the limit, just look at on the graph. Of course, we can solve for the equation and find all the intersection like we did before. But whatever you find the limit, make sure you actually graph it and see if that is the portion that we want. Right. So that's the first part. Of course, the area of the whole thing, after we do integrate those two, we add them together, we have the total area. Because the integration of this is kind of complicated too, so I don't want to get lost in the integral. My focus here is how to set up the integral, because that's more important than the integral itself. Right. Second, the area of the region inside the circle, outside the carioid. Inside of the circle and outside the carioid. Okay, I should give this. So I'm going to draw the circle and the carioid again. place the compass. So I have r equal to 1, and then the cardioid that could be better. So let's see, what do we want the area? Inside the circle and outside the cardioid. Inside the circle, but outside the cardioid. So we talk about that area. So again, because of the symmetry, we can cut this in half and multiply by 2, right? Because the upper half and the lower half, those will be the same. So first, let's say 2 times the area of that. I said kind of difficult to describe it, so I just draw. No, the area is equal to 2 times half of it. So the area of that is equal to 2 times the area of half of it. Right, so instead for the area of the whole thing, we cut that in half, upper half and lower half, and then we do that. Now we set up the integral of a half. First of all, what will be the limit? By the way, we kind of did this earlier. We say from pi over 2 to pi, that gives us that portion, right? Let's see that again. If we want the function 1 plus cosine theta, the cardioid, from pi over 2 to pi over 2 to pi, we have this graph. So from pi over 2 to pi, how about we have the other function too? Let's graph that as well. So in this we have that portion. So suddenly that check out from pi over 2 to pi, that integral. Now we just need to find the outer radius and the inner radius. Formula has 1/2 and again outer radius and then inner radius. Right, so in that case we look from the center. So can I zoom in here? Cannot really zoom in, just do the old-fashioned way. Right, better. Now looking from the center out, from the center, looking out in every direction. Of course, we only go from pi over 2 to pi. So when we do that, notice what we see first is the carryoid. The red curve is, when we go from the center all the way on the outside, we see the red curve, the carryoid. And after that, we see the circle, right? So in that case, the first thing we see is the inner radius, the red one. The second we see is the outer radius, the circle, right? So that's how we set up the integral. This will be equal to 2 times pi over 2 to pi 1/2. Again, the outer radius is from the circle. And the inner radius is that. So that is the area of that portion. D. So set up the integral that calculate the area inside the inner loop. Of whatever that is, limison actually we have the graph. I'm just going to sketch this real quick. So let's actually see how it goes. Right. 2 plus 4 cosine theta. Let's see the graph. Where's that? Alright. Remember, we go from pi over 2 to pi, right? I mean, pi over 2 to pi, yes. What if we go from 0 to 2 pi? Check the graph. It starts from somewhere, and then there's the inner loop, and then the outside. So first of all, we have to set up to see where the intersection here is. So find the boundary, so to speak. So I equal to 0, find boundary. Just trying to sketch the graph first. 2, 4, 6. Because we focus on the inner loop, so I do draw that first. Good enough. So we let r equal to 0 find the boundary, and make sure actually we should check for derivative not equal to 0 as well. But because after we found the boundary, we actually draw on the graph, so we actually check that already. So usually just a function r equal to 0. So 2 plus 4 cosine equal to 0. So cosine is equal to 1/2, negative 1/2. And negative 1/2, what's that? That is two pi over 3. Yes. So theta is 2 pi over 3, or cosine x values negative 1/2. We have this point or this point. So 2 pi over 3 or 4 pi over 3 plus 2k pi. We're good. So from 0 to 2 pi we have 2 pi over 3 and 4 pi over 3. So let's graph that from 2 pi over 3. By the way, where's the graph? Right, let's go from 0 to 2 pi. See the whole graph first. Now if we only want from 0 to 2 pi, by the way, if we want to zoom out to see the whole limmason, then we see it. The difference between this one and the carryoid doesn't have a loop. This one has a loop. Now we have 2 pi over 3 to 4 pi over 3. When we graph, right, let's zoom in. Do we only have the inner loop though? Yes. So from 2 pi over 3 to 4 pi over 3, we only have the inner loop. So the area of this graph is equal to the integral from 2 pi over 3 to 4 pi over 3. And then let's see the graph. From the center looking out, we only see the graph. We don't see any inner function, right? So in that case, we don't have the inner function, just the outer function, 1/2. The outer function is the carryoid. Have no inner function. Right, do that, and we have the area inside the loop of a limmason. Alright, so if it is a written test, then I prefer to ask this kind of question where we just set up the integral. However, the final exam is multiple choice. I cannot ask you to set up the integral because the multiple choice is not a good question to ask on that type of question. What I ask for is something like a rose petal, something easier to calculate. Besides, this one is nice because you have to know the formula of the reduction of power. And if we want to check, just want to do this, sorry, I'm going to go back and forth. I say the area of this, a times the integral from 0 to pi over 4 of the function 1/2 times 4 cosine square I should put cosine in the parentheses. That cosine square. Yeah, just that. Did I miss something? I see. This is cosine of 2 theta, right? 2. Right, you have that, of course, is 2 pi. So, actually on the test you can just, at least you can confirm the answer that way. Right. But most important, what I really want to focus on is to set up the integral. From the center out, inner radius, outer radius. Right. I take 5 minute break. We continue at 10:11. By the way, I will send you the link for the collaborate on trial. So I will send the link. By the way, when the class is over, you sign up. There's a link that I will send to you right now. When we're done with the class, when we finish the lecture, I will answer a few questions. During that time, if you can get in, into that collaborate or on trial, if you sign in to that, I will add 2 points to your final exam. And this is actually 2 reward for your being here. So once again, I'm going to send out the link now, and when we finish, probably around 11, if you get in, if you can sign in to that, and I write your name down until the end of the lecture, to the end of the stream, if you can sign in, I add 2 points to the final exam. Alright, so how do we add 2 pi over 3 to 4 pi over 3? If we set the calculator in degree mode, when we do cosine inverse of -1/2, we have 120 degrees, which is this. So we have 120 degrees. And the other one from here also have the same cosine of -1/2, and this is 240 degrees. Yeah, so 120 to 240, which is 2 pi over 3 and 4 pi over 3. Yeah, so should find a boundary for those first. Right, I'm not going to mention on when I send out an email, when I send out the link. But if you can get it, like I said, at the end of the lecture, until the end of the stream, when I try to answer the question, if I see your name in that, I'll add 2 points to the final. And that's probably not enough. How about 3? Yeah, 3 points to the final. Same class, okay. Where was that? Okay. Okay, we have that. Yes, I'm going to send it now. Perhaps you didn't get that email. Sorry. Let's try that again. Oh, shoot. Sorry, wrong one. Right, I send the link. The name for the email is testing link only. Like I said, if you can get it, sign in on that form when the lectures end, and then when the stream end, I'll add 3 points to your final exam. Right, do not get in now, but let's wait until when we finish on the section first. Right, so with that we go to the last section, connect section. This is library count, actually. Yeah. So the nice thing about the Collaborate Ultra is that is a very light service, very light software. It's unlike Zoom, you have to download Zoom. But this one, you just click on the link, and if you use your cell phone, click on the link, enable the camera, enable the microphone, and that should be good. Good to go. Connect sections. Right, Even though this is extremely long, but I'm not going to write everything out. Just focus on the conic section itself. Right, A, definition. Right, it says that, okay, it's extremely long. If we have a double cone, this in 3 dimensions. If we have the double cone like this, and we intersect that with a plane, and whatever the intersection is, we call that a conic section. The intersection of the cone, well, not the double cones, not the inside of the cone, but on the surface of the cone and the plane. The intersection is, in this case, is an ellipse. But that is a definition. So conic section, definition A and B is intersection of a double cone with the plane. And that we will go a bunch of different conic section. First one is parabolas. Like I said, this is just pre-calculus. Definition. Once again, the picture tells 1,000 words, so I just want to draw it. So what we have is, we have a line, and this line is called a directrix. And there's a point, that point called the focus. So we have a focus and a directrix. A parabola is the set of all the collection that equidistant from the focus to the directrix. For example, if we talk about this point, if we go to the focus and to the directrix, that distance will be the same. So that point is on the parabola. Talking about this point, distance to the focus and distance to the directrix are equal. So that points belong to the parabola. Same thing here. This distance, same as that. And by the way, we have the parabola like that. So this is a parabola. Again, equidistant to the focus, distance to the focus, and the distance to the directrix are the same. That is the parabola. And where the midpoint between the focus and the directrix, this point is called the vertex. And the distance from the vertex to the focus, distance is called A, and that is also A. So A is from the focus to vertex, or from vertex to directrix. And the equation will be given by that what we have on the table there. So either, and if we say if the vertex is at the center, then that doesn't make any sense. By center, I mean the origin. Then we have the equation x equal to in the note we use P, let's just use A instead. Let's stick with it here, so we just call it A, more like in breakout. So either we have x squared equal to 4a y, x squared negative 4a equal to negative 4ay, y squared equal to 4ax, y squared equal to negative 4ax. Right. If we live with y squared, it cannot be a function. So this one is a horizontal. If we have x squared, that is vertical. And it's positive, it go to vertical, so this one open up, this one open down, this one positive open to the right, this one open on to the left. The proper that is. So it is easier to try to graph it instead of, if you want to describe, it would look like in the note. But I use A here instead of P. One more thing though. The distance that go through the focus and intercept the parabola, that distance here is called the length of the lattice rectum, which is 4a. Rectum, the length is equal to 4a. Right. This is B. C. Example. Find the focus and the directrix and sketch the graph. For y squared equal to negative ax. Right. So first, this equation we compare to one of this form, and that will be this one, open to the left. So this is horizontal and open on the left side. We compare the two equations together. And from here, negative a equal to negative 4a. So a is equal to 2. So what does that tell us? Well, let's look at the graph. This one open to the left. So make sure there's enough room on the left for the graph. Right, so this problem, the vertex is at the origin, so we know the vertex is here. Open to the left. So when it open to the left, the focus have to be on the left. So it's nice to have the formula though, but even better if we can actually see what the parabola looks like. So 2, what is that 2? So 2 is, so A equal to 2, which means the focus to the vertex is 2, and also from the vertex to the directrix is also 2. Since it's open to the left, the focus will be 2 units away from it on the left. So here will be the focus. Of course, if we go from 0, 2 units to the left will be -2. So that is the focus. The directrix is the opposite direction from the focus. So the directrix will be go through this point 2. And so we have the directrix. And the directrix equation is x equal to 2. And the parabola open on the left side. So of course, how do we know if it is very skinny or very big? Right. That's what the length of the lattice rectum will give us. Whenever it go through the focus and parallel to the directrix, the length is going to be 4 times A. So it's going to be 8. So the length of the lattice rectum is 8, meaning that from here 4 units up and 4 units down. So that's how wide the parabola is. So that is the sketch of the parabola. So the focus is at the point -2, 0, and the directrix x equal to 2. Right. So we kind of have to just graph it at the same time as we find the other information. Two. Find the equation of parabola with the vertex at 0, 0, opens downward and go through the point 2 and -3. Right. So it's open downward, right? So first we have to find the form of the equation. Right. The one that open down is x squared minus 4ay. Right. Right, so we have that. When x squared equal negative 4ay, that's good. How do we find a though? Of course, the information we are given, we need to use them. 2 and negative 3. So put 2 in for x. And negative 3 in for y. A we don't know though. This is down, right? So negative. And y is negative 3. Right. So once again, the parabola that open down negative 4ay. So negative 4ay. And x is 2, y is negative 3. So do that. 4 equal to negative 4 times negative 3. That's positive 12a. Divide by 12. A is 4 over 12. It's 1/3. So a is negative. A is 1/3. Put it back into the equation. So x squared equal to negative 4 1/3 y. So that is the equation. So simple enough. One point, just one point is enough for us to solve for a. Right, that's good. Right, application of parabola. If a ray that go through the parabolic surface, it will go through the focus. At the same time, if we omit a line from the focus, after it strikes the surface, it will go parallel to we don't really have that axis, but that will be parallel to the line go to vertex and focus. So this is very important. We use this a lot in physics, especially in satellite, to intensify on the signal go through parallel to it. When it hit the surface, go through that. At the same time, if we put the light source here, and it will be parallel. So this, when we try to make the line to go extremely far and parallel, that's what we do. And at the same time, if we put this under the sunlight is parallel, and when it hit the surface, it will bounce off and it hit on the focus. So if we put something here on the focus in the direction line, that point will get extremely hot. Right. Let's go to second conic section, ellipse. Definition. Right. Once again, a picture tells 1,000 words. Actually, I have a ruler that can draw the ellipse. So let's do that. So first, let's draw the axis first. Right, as so this is an ellipse. Right. Now, how do we define an ellipse? So an ellipse, never mind. Right. So for an ellipse, the definition is if we have two focus that are plural will be two foci, F1 and F2. There are two foci. The center will be, in this case, at the origin, right in the center, in the origin. Now, the definition of the ellipse is all the points will go from one vertex or one focus to another focus. The total distance is constant. So the total distance will be the same. So if you add that to that, it's always a constant. Whether the points here. So the total distance from a point to two foci is constant. We run out of time. Otherwise, there's a lot of cool YouTube video. If you have a pool table in elliptical shape from one focus and one focus, if you put the ball in one focus, doesn't matter where you hit when it strikes the surface, the parabolic surface, it will go through the other focus. Again, you have the ball at a focus. When it hit, it will bounce off the other focus. It will go through the other focus. But the definition is the total distance. The total distances from a point to two foci are the same. Right. So that's how we defined ellipse. So I just said total distance from a point, any point, this the total distances from a point to foci are the same. So add those two distance will be the same. That's the definition. Right. In terms of ellipse though, how do we actually draw this? So B ellipse where center is at 0, 0. Right. There will be two cases, the one that is horizontal and the one that is vertical. So one is horizontal and one is vertical. Since I have the ruler, better use it. Choose a bigger one. Okay, this is nice if we have a ruler like I have there. But if we don't, how do we graph it? Right, the way we graph this is we draw a rectangle around it. So we draw a rectangle around it. This is a rectangle. So obviously this one is horizontal, that one is vertical. Okay, no big deal. But the way we graph this is, if center is at 0, 0, then whatever the horizontal distance is, let the bigger distance be A. So this will be A, negative A, B, negative B, A. So the bigger distance is A, the smaller distance is B. Right. So the equation is the horizontal distance is A. So in that case, we're going to put A squared below it. And the vertical distance is B, put B squared below it, equal to 1. Similarly, here the horizontal distance is B, put B squared below X squared, and vertical distance is A. Right, so whenever the longer axis, the one that the maximum distance that go through the center touch the focus, this is called the major axis. So this one, the major axis, is going to be vertical, and the other one is the minor axis. The interesting thing about this is the two foci are on the major axis, and the distance from the center to that is called the C. And in general, out of A, B, and C, C is the longest distance, so we have C squared plus B squared equal to A squared. And we have two foci, F1, F2. And then the furthest point away from the center called the vertex. Right, C example. First, find the vertex, foci, and the length of major axis, minor axis. Well, there are a lot. Vertices, two vertexes. Foci, length of major axis, and minor axis. Graph the ellipse. X squared over 9 plus y squared over 4 equal to 1. So actually we're going to graph it first and then determine the rest later. Right, so if we have the equation, that the first thing we graph, take the square root of that number 3 and square root of that number 2. The 3 under the x, the 2 under the y. So in that case, we have 3 on the x-axis, 3 to the left, and 3 to the right, 2 under the Y, 2 up, 2 down. So let's make a box. So draw the box, 3 left, 3 right, 2 up, 2 down. And the ellipse will fit inside that box. I try to find the best, draw the best we can. I cannot really use this one because even though I can find one of them fit, it's not enough because this have the fixed ratio of major and minor axis, so this one doesn't help at all when to draw a particular ellipse. So something like that. So first, on this one, the center obviously is 0, 0. That even though it did not ask, but we can say right. Now, by definition, the furthest point away from the center is the vertex. So in this case, we have 2 vertices, 3 left, 3 right. So 3, 0, negative 3, 0. And then because of that, the distance from the vertices, the major axis, the one that is bigger, is negative 3 to 3 is 6. The other one is negative 2 to 2, which is 4. So major axis, distance from vertex to vertex, 2 times 3 is 6. Minor axis, 2 times 2 is 4. And the foci. The foci will be aligned on the foci will be on the major axis, and the distance from the foci to the center, we call that distance C. Distance is C. And here we can call one of them is A, the other one is B. The bigger one is A, the smaller one is B, and we can find C. So Petal theorem, C squared plus B squared equal to A squared. Not quite the Petal theorem, but the biggest one square is equal to the sum of the square of the other two. So in that case, we can find C equal to plus or minus square root of A squared minus B squared plus or minus square root of 3 squared minus 2 squared plus or minus square root of 5. Actually, we should say C just square root of 5. But with that, we can find the foci. The distance away from it is negative square root of 5 and square root of 5. Square 5 here. So the foci in this case, negative square root of 5, comma 0, square root of 5, comma 0. Two. I think I stop after this example. Right, find the equation of ellipse. center at the origin. With foci on the x, on the y-axis. Major axis is 8 and minor axis is 4. But put all of this information together. First of all, center 0. Right, that much we know. Next, foci on the y-axis. So it's not going to be horizontal, it has to be vertical. So foci on the y-axis, this gives us, this is a vertical one. And the major axis is 8. If the total is 8, from the 0, 4 up, 4 down. So that gives us the major axis is 8. And then the minor axis is 4, the other one. 2 left, 2 right. So that's pretty much it. If we want to graph it, the ellipse is going to be the skinny one. But the equation though is x squared over something plus y squared over something equal to 1. And what we put for in between here is below the x-axis. There 2 left, 2 right, so we're going to put 2 square there. And the 4 up, 4 down, so it's going to be 4 square. So the major and the minor axis give us A and B, and from that put in the equation, we have the equation on the ellipse. The reason we know which one is vertical, which one is horizontal, because on this one, foci is on the vertex. All right. Next we have hyperbola. So if we define the total distance from a point to two foci, if the sum of two distance, the sum of two distances are constant, then we have an ellipse. The hyperbola is where we call the difference. So difference between the distances to the foci is called the hyperbola. So in this case, what we have is 2 points, and if we take a distance the total distance, not total, difference, if we take the longer distance minus this shorter distance, if that is constant, the point belongs to a hyperbola. So the longer distance minus shorter distance, if that is constant, it belongs to the parabola. So take the big one minus the longer one. Right. So that is the definition. The rest I just going to put it on look at the note, because I just want to, I think we cover enough for calculus too. Again, it's in the note, and it's just like with calculus. So Like I said, I'm going to stop here. So at this point, you should stay on the video though. You can go to the link that I sent earlier and try to sign in the Blackboard Collaborate Ultra, and let's see if you can do that. Right. Right. Just want to show you this real quick though. So this is all the notes that we have for today. All of that. And for the whole class, including the review, we have this much. Kind of on the camera, kind of 1.5 inch probably. Even though I only write one-sided, but still a lot of notes. And if you've been here for all of that, so thank you very much. Like I said, there will be a lot ready. Now try to sign in if you can, and I will write out the name of that. Right. At this point, I try to first of all want to say thank you for actually being in class. I know it's very difficult to sign up for a lecture class and end up have to study like this. I'll try the best I can. Sometimes the technology is not where I want, what I hope for, but at least I try my best. And I'm sure you try your best too. So let me write all the name of the people sign in. Right. One more thing though. Right now I don't require you to set up the camera, but on the same day, you should be able to enable the camera so I can see you, because on the test we need the camera to proctor. So I set up the camera. Sorry, cannot do that because I'm using the camera for the YouTube video here. Right, so I saw you good, so that's good. So make sure you certainly can do that, and on the test, make sure you have the cameras on. So when I see your camera, I can give you the password, and then you can check the test. So let's see what I have. Everybody names here, and there should be one more. All right. Even though I have more people on the YouTube video than I have on the room here, but anyway, I write all the name I see there. Right. Before I end the stream, do you have any question? Right. Remember, I sent you an email about the final exam, what will be on the final exam, and how to take the final exam. One of that is with the Blackboard Collaborate Ultra here. How do we sign in? And and then we take the test. Of course, on the test, you should be able to enable the video so I can see you. When I see you, I give you the password, and then you can take the test. The test is on eCampus. You don't see it now, but by the time you take the test, click on the final exam. Yes. If you see the chat, I will reply to each one individually. Yeah, so I got, don't worry, I brought all the name of the people that actually signed in now. Of course, on the test, just enable the camera and we can go from here. Actually, you were there, but then you left. Can you try to click on the link again? Yeah, I got a few people already in and sign out, but this is fine. Like I said, as long as you're in, you have the credit. Of course, when you got kicked out, you can always go back in. As long as you have the link, you can get back in with no problem. Yes, I also know that there might be some problem with it in internet, so maybe it's difficult to show. But I said the quality video, it doesn't matter as long as I see some picture. Right. Do you have any other question before I end the video? So, if you have no other question, then I will end the video here, and we'll see you on Friday if you're taking the test on Friday. Right. As always, if you have any question, just send an email to me. Other than that, good luck on your final. Yes, yeah, I think you in. If you can read the chat, I actually reply to your chat. Yeah, I type on the chat that I got your name down, so you're good. Right, so When I end the video, when I end the stream, I also end the Blackboard thing. So if you sign up to the link later, that will be inactive. You won't be able to get in because I close that section right after I'm done with the video here. Right. Let's end my video here. Right, I'm going to end the video here. Have a nice day.